Hello, my name is Yufei Wu. I'm a PhD student from Wuming University. In this video, I will present our work on bypassing dynamic taint analysis using a type confusion vulnerability. This research was accepted to the NIER track at ASE 2025. Here is a quick overview of today's talk. I will first give a brief introduction to dynamic taint analysis, what it does and how it's used. Then I will walk you through the core vulnerability we're exploiting, type confusion. After that, I will explain our approach and how the attack works in practice. Then I will show experimental results on two real-world tools, Phosphor and Tendroid. Finally, I will wrap up with a short summary. Dynamic taint analysis, or DT, is a runtime technique for tracking how sensitive data moves inside a program. This motivation is simple. Once private information enters the system, we want to make sure it never leaks to untrusted outputs. So DT attaches a taint tag to each piece of sensitive data. As the program executes, this tag propagates automatically through the system through the program's data flow. If the tagged value ever reaches a sensitive thing, such as a network send error or file write, the system raises an alert. Here is a simple example. Input from get user input flows through several variables until it passes to send to server. And this example here is simplified. In real systems, data flows are more complex, and that's why we need automatic taint tracking tools. This approach has been adopted in many real-world systems for privacy, security, and debugging purposes. So how is taint metadata actually stored? In many systems, including Phosphor, which we use in NIER attack, the taint tag is inserted directly inside the program object. This is known as the shadow memory approach. It's fast because it avoids separate data structures, but it comes with a cost. It assumes the layout of the object stays intact. Look at this example. It's a code provided by Phosphor. On the left, you see the original class. On the right is the transformed version after Phosphor instrumentation. Every value is paired with a tag field, and taint is propagated explicitly through tag arithmetic. This works well in practice, but only as long as no one tampers with object layout. Type confusion happens when a program misinterprets the type of a memory object. That is, it accesses an object using a type that's different from how it was originally created. This shows how one object can be interpreted in different ways. Look at the example on the left. The same memory can be seen as a long or as two ints. Type confusion lets us switch between these fields. And when we write through one, we silently change the other. In our case, it lets us access and overwrite internal metadata without violating the language's type checks at runtime. So this is the motivation behind our work. Dynamic taint analysis tools are built on a simple assumption. The memory layout is safe and consistent. But in reality, this assumption doesn't always hold. With type confusion, we can reinterpret the object layout and gain write access to the taint tag field. Once we override that memory region, the tag is gone, and the tool fails to detect the leak at all. Here is a high-level overview of our approach. We start with a program that contains a known type confusion vulnerability. Next, we run this program under a dynamic taint analysis tool, such as Phosphor or Tendroid. These tools insert taint tracking logic during instrumentation. At runtime, we exploit the vulnerability to perform a layout reinterpretation and use it to override the turn tag of a sensitive variable. As a result, the tag is already gone before the data reaches the sink, so the tool never raises an alert even though a leak occurs. Let's look more closely at how we exploit the type confusion in memory. In the setup, we define two classes, A and B, with compatible layouts that can overlap in memory when reinterpreted. For example, class A contains an integer field, plus an invisible turn tag automatically inserted by the analysis tool. Class B has a single long field. We exploit this by casting an object of type A into type B and writing to b.p. Because the long takes 64 bits, writing to b.p overrides both a.p and its hidden tag. From the JVM's perspective, this is perfectly valid. We are writing to a well-typed long field, so there is no crash, no type error, and no alert from the analysis tool. But in reality, we have silently erased the turn tag stored in the second half of that memory region. We evaluated our approach on two widely used dynamic taint tracking systems, Phosphor, which runs on the JVM, and Tendroid for Android. For each system, we run two versions of the same program, a baseline with taint flowing from source to sink and an attack version with type confusion injected. The goal is simple. Can this tool still detect the tainted data once memory has been reinterpreted across object types? This is the result. Both tools tracked the baseline flow but missed the attack variant due to tag corruption. To summarize, first we demonstrate how type confusion can be used to silently corrupt taint metadata without violating the type system. Second, we applied this technique to two real-world taint analysis tools and successfully bypassed both under their default configurations with no alerts and no crashes. And finally, our main takeaway is this. Even trusted runtime systems can fall if they rely too heavily on assumptions about the memory layout. That's a quick look at our work. Thanks for watching, and feel free to reach out if you'd like to discuss more.